So we got like what are the pressing optimization vectors for hydrogen engines. So, but here I will be pressing for a case while we have a limited supply of the hydrogen. So how we can take gains so that at least this motivation for continued usage is there. So this introduction I will skip, but I would like to spend some time for EV selling scenario in India in just concluded quarter. So it is very well understood that there is no competition among EVs and say engines in the case of, yeah, okay, so for commercial vehicles, so there is nothing even available in the market, and even for say passenger cars, so just 1.68% was the electric vehicles. But there are say some big numbers coming, so they are primarily these 3 vehicles and some 2-wheelers. So they are making this apparent number of EVs up to say less than 6%, but they all are coming from 4-wheelers and 3-wheelers. And if we consider that contribution of emissions in the transport, it is the amount of fuel burnt. So more than say 90% fuel is being burnt in the larger vehicles. So then if we have to make some effort for reducing emissions through transport sector, so alternate fuels along with the EV, they are there. So even suppose there is not the availability of 100% green hydrogen, so if we are say even substituting by 10%, 30%, so if there is at least 30% reduction, so at least this should continue. So with that objective, like in the past we have seen in India, due to market driven scenario, fuels like LPG, CNG, they were really very, very popular. So same way, if there is a national mission for hydrogen, and there they are claiming that significant increase in the hydrogen production will happen. So even limited availability of the hydrogen should even be used and process should continue. And then we can think of this quantum jump, because nowadays on roads, IC engines, they are giving say efficiency in the range of 15% and 20%. In the previous presentation, we saw that 47% is achievable. And if there is long range of the flammability limit for hydrogens, so then even we can ensure that those higher efficiencies can be achieved even at part load condition. So if those numbers they are put in proper context, so that efficiency improvement with proper optimization of the say hydrogen engine vectors, so we can have at least say 50% reduction just by utilizing these hydrogen engines to its full potential. But then at least this continued effort should be there, even without say 100% hydrogen substitution due to availability scenario or the storage scenario, partial usage should continue. Then even this exhaust heat recovery, it has potential of about 2 to 3% improvement in the efficiency, and if it is coming through this hydrogen route, exhaust heat recovery first converted into say onboard hydrogen production, and it can be put into say combustion chamber. So then it attempts to surpass those storage challenges. So in that context it is mentioned. So along with engine optimization, this exhaust heat recovery by surpassing the storage, it can help out. So with that objective, what results I will be quickly presenting, they are related with what is the effect of say up to 10%, 20%, 30% hydrogen energy substitution in diesel engine. So that has one direct advantage, that here we have say advantage of higher compression ratio. So then efficiency numbers what we should be comparing. So we get the advantage of these higher compression ratio compared to the normal gasoline engine. But of course, because that engine is not designed for operation on the hydrogen, so there are some problems as well. So listing of those problems will of course form basis for further discussion. So with that objective, I will be quickly showing some interesting and unsolved results only. And here up to say 30% hydrogen energy share along with 10% exhaust they were used, and how it affected the engine performance and emission along with as noise vibration characteristics that I want to highlight. So as in the previous presentation, we saw that the gas-gas mixing is a challenge. So even in the diesel engine, we go for this say up to 30% hydrogen intake. So it shows that pressure rise is delayed, heat release rate becomes lower. So all they are indicating that though diffusivity of the hydrogen is higher, but in the conventional diesel engine, it has huge challenges to get even proper mixture, because there is tendency of stratification in gas-gas phase. So at lower loads, at 25%, those differences are there, but say they are pronounced even at the say 100% load condition in that particular engine. So then how they affect the combustion phasing and peak pressure. So it appears that these two effects, this hydrogen addition, it tries to compensate for the loss in the peak pressure, which is caused by say some amount of the EGR. But this EGR and hydrogen, they were simultaneously studied just to see how much that particular engine is deviating in terms of emissions and performance. So but from here, we can simply have this small conclusion that while we are going to have some EGR, it is reducing the peak pressure, but substitution of some of the diesel with hydrogen is able to compensate that. So at least there is not much difference in peak pressure and combustion phasing represented by the location of the peak pressure. But then coming to cycle variability, so there are say of course significant increase in the cycle to cycle variability while we are operating that engine at lower load as indicated by this COV of Pmax and IMEP, but those numbers, they are in acceptable limit while we are moving to the higher load, the graph indicated on the right one. So I will skip this. So then coming to how this stratification of the combustion and higher laminar velocity of the hydrogen contributes to increase in the engine noise and vibration. So this was measured by just a simple accelerometer test and separating out the noise and vibration in the motoring condition and in the fired condition. So here we can see that the conditions represented on the farmost right. So there we say that while we are going up to 30% hydrogen energy substitution, so this higher laminar velocity of the hydrogen, so rate of heat release is not smoothly transferring to the useful pressure rise. So that is doing harmful effect of increasing the vibrations and the say combustion noise increment. But if that effect can be suitably utilized by tuning the engine say piston speed with respect to the flame speed of the this different fuel hydrogen, so then I think by those improvements we have scope for even surpassing this 47% limit. So in response to the question so I would like to say that hydrogen is altogether very different fuel. Whatsoever knowledge we have gained for this gasoline, diesel, and whatsoever capabilities we have developed for engine research and diagnostic, they needs to be used to tap this higher flame speed so that we can even challenge the efficiency promised by fuel cell engines. And yesterday from French delegation, I heard someone is working on that perspective, like they take this fuel cell as a benchmark and claim that we should be pushing the engine design so that even IC engines should come into competition with that. So then what appears as a problem mismatch in the, say, design of the engine for slower fuel, and so proper stratification and say some other changes in the design, we may even challenge that. So then usual issues, of course, if there is a gaseous fuel in the engine design for some other purpose, so this volumetric efficiency reduces, but hydrogen doesn't need as much surplus oxygen what is needed for diesel, so that's why that was not a big problem. So here if we see this efficiency numbers, so at least we can say hydrogen was able to catch up even up to 30% substitution with the corresponding diesel efficiencies. So those efficiency numbers, but missing carbon content, of course, resulted into CO2 emission reduction. So maybe it is better to see like what was the, say, overall effect. So with this proper tuning of the say EGR, so even this problem of say increase in the NOx was not there. So even NOx reduced by, say, 35% compared to engine where only diesel is fueled without EGR, and the situation where there is EGR plus 30% hydrogen, and then there is a reduction in say other pollutant. And just to give context to like these numbers, so we are substituting, say, up to 30% hydrogen. So like best optimized condition is to have gains more than 30% reduction, but because that engine was not optimized for hydrogen, so even in say crude engines, so partial substitution what can be achieved, those numbers are showing this. So one say non-regulated pollutant, so AHC that reported some increase, so that is a cause of concern while thinking of this partial substitution. So then coming to summary, so if as an intermittent say strategy where availability is not there and there are, say, associated challenges of storage and range anxiety is there, and if this like something pick up in the decentralized say hydrogen generation like biological routes and other things are there, so we should have even intermittent strategies to go for even this partial substitution. So there it appears that proper tuning of simple strategy of the EGR, so at least up to 30% substitution is there with the gain of at least say that 30% reduction in the CO2. And of course there are gain in the some final emissions as well. So maybe 1 or 2 minutes I would like to spend on the road ahead or future perspectives. So I see that like if we have gained lot of knowledge in 150 years in engine design, and now these optical diagnostic techniques, so that even we are able to see the near wall combustion effects. So it is possible to challenge like what is the efficiency for these fuel cells by going really lean, but of course the volume occupied by this engine for these conditions, they will be much bigger than the way we are currently thinking. But for large vehicles like trucks and marine applications, I think increasing the size by say even double or having large scale turbocharging so that we can operate really lean. And also now we are thinking to challenge the irreversibilities by even thinking of say flameless combustion, so that there is not much stratification inside the combustion chamber. So even the efficiencies should be targeted in that higher range. So this higher laminar velocity should be taken as a advantage, so that this thinking of this part load, this responsibility should be given to some really flexible control system, and it can be as radical as even like in multi-cylinder, some cylinders can be even put to the off mode so that we are near to the most optimized condition. So with that, I will stop and maybe some.
Thank you for the presentation. Simple question. Was there a limit to go for higher hydrogen content? Because you increased up to 30%. So was it not possible to go for 50, for example?
So it was limited by say my experimental capabilities and resources to modify the engine. Okay. So purpose was simply in unmodified engine what can be tolerated.
Okay.
Yeah.
So okay, as a retrofit without changing.
Yeah.
Okay.
And for retrofitting and advancement capabilities, it was already presented in previous one.
A small query. You mentioned about that AHC increase.
Yes.
So what's the any underlying reason identified for this? Because it is not supposed to be increasing. Hydrogen, but is there any?
So one thing, even this study was not capable to give any insight on the mechanism, how this small hydrogen and diesel fuel is interacting. So I don't think I am in position to comment on the actual mechanism.
In literature or somewhere there is.
So in literature, I think.
Identified the cause for this increase because.
So in literature, there are not much studies on this. Going for this putting the diesel along with hydrogen, because in some way it is also objectionable putting one comparatively clean fuel with bad fuel, but partial substitution, partial gains, there that strategy is useful. And maybe so there may be say some localized region, there are say increase in the interaction between this diesel aromatic content and this hydrogen reaction, but that may be some indicator but not exact answer.
What is happening to your suit?
Yeah. So for suit there was something, but I skipped. So suit is reducing. So at least here it is even more effective than that 30%.
Ash was asking for, that is it happening like this, that your unbound carbon, which were formed in soot earlier, that is now getting some amount of hydrogen to increase the amount of HC.
Yeah, so that may be
one mechanism.
Something oxidizing and.
Because unless you were really study the mechanism in detail, it's difficult to say.
Yeah.
Maybe that is the reason.
So I have one question is that with increasing concentration of hydrogen, basically you told earlier that there is a reduction basically in peak pressure as well as heat release rate, but there is an increase in vibration as well as noise within. So because generally with decreasing in pressure, there is always reduction in noise and vibration. So what are the reasons behind it?
Yeah, so the context, suppose we are dealing with the fuels that are having comparative say laminar flame velocity.
Okay.
And there are causes like say some chemical advantage like oxygen content and other. So a small pressure rise typically that is
so you also basically
reducing
pressure
so a small reduction in pressure rise but accompanied with say higher vibration.
Okay.
So then that's why it indicates that there is not proper match between the say flame propagation and the piston movement speed.
And there is also in emissions there is also one component that should be investigated, that is unburned hydrogen. So is do you measure?
So in this study it was not measured.
Yeah, but do you think how it should be? What by literature or anything, what should be the contribution of unburned hydrogen?
So at least I saw in the previous study. So this NOx as well, this H2 they were measured. So due to this very small quenching distance of hydrogen, so they were reported almost say 0.
No, but I think there should be some hydrogen.
As long as say there is no properly designed injection system,
Because
in combustion it will not be problem. So like mechanism hydrocarbon emission in gasoline and others, so that will not play here thanks to this small quenching distance of hydrogen.
Thank you. Thanks again.
Long live India and France friendship.